Okay, here's a little review of related rates. I've got a couple of examples here of kind of classic related rate questions. The first one is talking about the area of a circle and the fact that it's increasing because the radius of the circle is increasing at a rate of 3 centimeters per second. The question is, determine the rate at which the area of the circle is changing when the radius is 10 centimeters. So we've got this circle that's going to be getting bigger and bigger and bigger because the radius is getting bigger, of course. So I'm going to draw a really lousy circle here just to give us an idea. And we've got this radius here that's getting bigger, and of course it's going to affect the area of this circle. So the way to get started with these problems is come up with a fundamental relationship that relates the two things that we're talking about. We're talking about area and radius, and that's couldn't get much more fundamental than that. The area of a circle is pi times r squared. And the next step is to simply differentiate both sides. Well, the next step is to make sure that you only have variables which are accounted for in the problem. There are problems where you might have a cylinder that's getting bigger, but they're going to tell you something about the relationship between the radius and the height of the cylinder that might get rid of one of your variables. Well, this is very simple. We've got information about the radius and the rate at which the radius is changing, and they're just asking us about the area changing. So the next step is to just differentiate both sides with respect to time. So the derivative of area with respect to time is dA dt. And then remembering that pi is really just a constant, the derivative of pi r squared is just bring the 2 down in front, which gets multiplied by the pi. You drop the power of the radius to 1, and then you go and take the derivative of what's inside, being the radius, and that with respect to time, and that's dr dt. So now we just have to make sure we have all the information. We've got a radius being 10 centimeters. We're going to plug that in there. And we've got the rate at which the radius is changing right there. And of course, that's going to leave us dA dt. So dA dt is simply 2 times pi times the radius, which is 10, times 3, which is the rate at which the radius is changing. So to clean that up, we would say, what is this? 2 times 10 times 3 is going to be 60 pi. As far as the units go on that, because the area is measured in centimeters squared and time is being measured in seconds, the units would be centimeters squared per second. So that's a very straightforward related rates problem. They could do the same, basically give you the same kind of problem and ask you about how fast the radius is changing if they gave you the rate at which the area is changing. So in that case, you would have dA dt, and they'd be asking you for dr dt. Probably the all-time classic related rate problem is the ladder problem. We've got a ladder is leaning against a house that's 15 feet long, and the base of the ladder is sliding away from the wall at 2 feet per second. And the question's asking us how fast is the top of the ladder sliding down the wall when the ladder is 9 feet away from the house. So you should remember these kind of problems. This is basically a right triangle, so it's going to be like a Pythag thing. So we're going to label the vertical piece y, the horizontal piece x, and we can say that x squared plus y squared equals 15 squared. The fact that you may or may not know what 15 squared is doesn't really matter, because the very next thing we're going to do is take the derivative with respect to time. So we'll bring the 2 down in front, 2x, and take the derivative of the x with respect to time, dx dt. The same thing with y, 2y dy dt. And then the derivative of 15 squared is, of course, 0. At this point, we could plug stuff in, or we could realize that we have a common factor of 2 in every term. So why don't we just delete those 2's, divide everything through by 2. Dividing 0 by 2 is still 0. And now we have a much simpler formula. And we have information about the base of the ladder being 9 feet from the house, so we know that x equals 9. We know that it is sliding out at 2 feet per second, so that would be dx dt is 2. But we don't know what y is, and they're asking us what dy dt is. So we have a little bit of an issue unless you remember our original equation has x squared plus y squared equals 15 squared. So we can let x be 9, say 9 squared plus y squared equals 15 squared. And we're going to realize that 9 squared is 81, 15 squared is 225, and so y squared is going to be 225 minus 81, which is 144. So y is going to be 12. We know it's not negative 12 because it's a length. So now that we have the y value, we can plug that into our function, and we get x is 9, dx dt is 2, y is 12, and dy dt is what we're looking for, and that's equal to 0. 9 times 2 is 18, plus 12, dy dt. Subtract 18 from both sides, and you're going to get 12 dy dt equals negative 18. Then divide by 12 and divide by 12, and you get negative 18 over 12, which reduces to negative 3 over 2. So we can say dy dt is negative 3 over 2, and that would be feet per second. So that means it's sliding down the wall at 1.5 feet per second, or 3/2 feet per second. There you go.